Hello everyone, in this video I'll be talking about IR spectroscopy, and I have made one video about IR spectroscopy on my YouTube channel. If you haven't watched that video, please watch it out. Or if you are already familiar with IR spectroscopy and want to learn more about it, and please continue watching this. And in this video I'll be talking about modes of stretching and bending. So the simplest type of modes of vibrational motion in a molecule that are infrared active. Those that give rise to absorptions are stretching and bending modes. So this is a stretching and this is a bending mode. So as you know that molecules when vibrate, they have several type of modes of vibration, and in IR we consider mainly the stretching and bending modes. In order to clarify the modes of vibration, let me show you this figure. So this is symmetric stretching, this one, top one. As you can see that this is a orange yellow atom, and these are the blue atoms which are both coming down and going back. As you can see, this one is now coming back and going back, and that's the symmetric stretching. So at the same time, both blue balls or blue atoms are coming down and going out, or coming in and coming out. But if you look at the asymmetric stretching, if you can clearly see that one ball is coming down and another one is going back. So consider these blue balls as atoms, and now this one is coming down and this one is going back, and this is asymmetric stretching. Now this is wedging. As you can see that in wagging, like both balls are at a time, they are coming towards and coming away. So they are coming towards the front side and going back on this side. This is a wedging mode of vibration. Then this is twisting. So this is one atom is going back and another is going forward, and one is going back and another is going forward. And this is scissoring. It's like a scissor. So they are cutting like scissor cuts the things. Then these atoms do vibrational via scissoring. And another one is rocking, where it's related to like a song. When we listen to the music, we do rocking moments and waving hands like up and down, left and right in the air. So these are the 6 modes of vibration: symmetric stretching, asymmetric stretching, wedging, twisting, scissoring, and rocking. Now, how to calculate number of vibrational modes? This is the formula for linear molecule 3n-5, and this is a molecular formula for 3n-6 for non-linear molecules. So for example, carbon dioxide is a linear molecule, so it has there are total 3 atoms in this molecule. It is a linear molecule, so we use equation number 1, that is 3n-5. So 3n equals to number of atoms, 3 times 3 equals to 9, minus 5, so 9 minus 5 equals to 4. There are 4 modes of vibration exist in carbon dioxide. So if you see here the carbon tetrachloride example, or methane. So in this molecule there are total 5 atoms, so we put 5, 3 times 5 is minus 6, so 3 times 5 is 15, minus 6 equals to 9. So buckyballs, vibrational modes. So in this molecule there are total 60 carbon atoms. It's a non-linear molecule, so we will use a different formula, that is 3n-6, and there will be a 160 modes of vibration for buckyballs. So this is how you can apply these 2 molecular formulas for linear molecules and for non-linear molecules to calculate number of vibrational modes. And the possible vibration modes that exist for a molecule are 6. One is symmetric, another asymmetric, one is wagging, twisting, scissoring, and rocking. So these are the 5 important 6 modes of vibrations. That exist for molecules. Now let's go back and understand more detail. By the way, I'm following the video, following the notes from the Pavia introduction of a spectroscopy book, and we were discussing modes of stretching and bending, and from the internet I showed you that there are 6 modes of vibration, and I also mentioned you how to calculate the modes of vibration by using 3n-5 formula, and also so this is the this one is the stretching and this is the bending. So in bending we observe the bending of the molecule from this to this, and in stretching it's stretch this way as well as this side. Okay, so that's the 2 bonds. So however, other more complex types of stretching and bendings are also active. So IR active are those which are, these are called IR active because they are being observed in are detected by IR. So stretching and bending vibrations are the most important in IR, so we call them IR active vibrations. The following illustrations of the normal modes of vibration for a methylene group introduce several terms. In general, asymmetric stretching vibrations occur at higher frequencies than symmetric stretching vibrations. Also, stretching vibrations occur at higher frequencies than bending vibrations. The terms scissoring, rocking, wagging, and twisting. So these terms I explained to you just earlier. Scissoring, rocking, wagging, and twisting are commonly used in literature to describe the origins of the infrared bands. So in any group of 3 or more atoms, at least 2 of which are identical, there are 2 modes of stretching, either symmetric and asymmetric. So examples of such groups are CH3, CH2, NO2, NH2, and anhydrides. The methylene groups give rise to symmetric stretching vibration at about 2872 per centimeter and asymmetric stretch at about 2962 per centimeter. So the CH2 signal methyl group, CH3 group gives signal at these 2 regions. The anhydride functional group gives 2 absorptions in the CO2 region. This is a carbonyl region because of the asymmetric and symmetric stretching modes. A similar phenomena occurs in the amino group, where a primary amine NH2 usually has 2 absorptions. That's key point. 2 absorptions in the NH stretch region, while secondary amine has only 1 absorption peak. Amides exhibit similar bands. There are 2 strong NO stretch peaks for nitro group, with the symmetric stretch appearing at about 1350 per centimeter and the asymmetric stretch appearing at about 1550 centimeters. So again, I'm opening these sort of vibrational modes so you can calculate, you can understand these ones. So I stopped the screen for you to understand these symmetric stretch, which occurs for CH2 at approximately 13, 28, 35, 53 per centimeter. Scissoring for CH2 occurs at approximately, this is approximation sign, for 1450 per centimeter. Wagging occurs for wagging 1250 per centimeter. And there is a asymmetric stretch, which in this case the peak appears at 26 per centimeter. And there is a rocking, which the peak for CH2 appears in rocking, that is in plane, at approximately 720 per centimeter. Hooke, this is called out of plane. So sometimes when you read IR spectrum, you see there's a Hooke, out of plane twisting, that is observed for CH2 at approximately 1250 per centimeter. So these three stretches, asymmetric stretch and asymmetric stretch, these are stretching vibrations, and scissoring, rocking, wagging and twisting, these four are bending vibrations. Okay, so two, symmetric and asymmetric, they are stretching vibrations, and scissoring, wagging, rocking and these four are two are stretching and four are bending vibrations. Okay, let's go on. Okay, for methyl, symmetric stretch gives the peak at 2872, and asymmetric stretch for methyl gives peak at 2962. In anhydride, we observe two peaks for this carbonyl group. One is symmetric and another one is asymmetric. Symmetric one appears at 1760 and asymmetric appears at, so in asymmetric one is going down and one in another carbonyl goes going up. So this is up, going up, and this is going down. So D O W N, down, and this is up, and both are up, as you can see from the arrows. So this is symmetric stretching because both arrows are going up. In this one is going down and another one is going up. So anhydrides, the carbonyl group of anhydride gives two peaks, one at 1760 and another one is at 1800 per centimeter. So two peaks for carbonyl, two peaks for methyl, and two peaks for amino as well, and two peaks for nitro as well. So for nitro group, that is NO2, when we write it, nitro group is just like this, NO2, and NO2, this is a symmetric stretch because this one is going outside and this one is also going outside. So the peak for nitro group, symmetric stretch peak appears in the IR spectrum at 1350 approximately, and the asymmetric, where one is going out and one is going in. Okay, so this is out, this is in, and the peak for nitro group appears around approximately 1550 per centimeter. So two peaks for methyl, two peaks for anhydride, two peaks for amino group, and two peaks for NH2 due to stretching vibration, symmetric and asymmetric. Let's discuss more. The vibrations we have been discussing are called fundamental vibrations, stretching and bending. Due to these two vibrations, we observe peaks in the IR spectrum. They arise from excitation from the ground state to the lowest energy excited state. Usually the spectrum is complicated because of the presence of weak overtone, combination and different bands. Overtones are result from excitation from the ground state to higher energy states, which corresponds to integral multiples of the frequency fundamental nu. For example, you might observe weak overtone bands at 2 nu bar, 3 nu bar. Any kind of physical vibration generates overtones. If you pluck a string on a cello, string vibrates with a fundamental frequency. However, less intense vibrations are also set up at several overtone frequencies. An absorption in the infrared at 500 per centimeter may well have an accompanying peak of lower frequency 1000 overtone. So when two vibrational frequencies nu1 and nu2, this one, in a molecule coupled to give rise to a vibration of a new frequency within the molecule, and when such vibration is infrared active, it is called combination band. It arises due to the combination of frequency 1 and frequency 2. So when these two frequencies of molecule combine, then you get CB, that is combination band. This band is the sum of two interacting bands, V1 and V2. Not all possible combinations occur. The rules that govern which combinations are allowed are beyond the scope of our discussion here. Difference bands. So we discussed combination bands, now we are discussing difference bands, or similar to combination bands. The observed frequency in this case results from the difference between two interacting bands. So you subtract frequency 1 from frequency 2, and the result that you get is V new difference. So combination is addition and difference is subtraction. So one can calculate overtone, combination, different bands by directly manipulating frequencies in wave numbers via multiplication, addition, subtraction. So if you multiply, you will get overtones. If you add, you will get combination, and if you subtract, you will get difference bands. When a fundamental vibration couples with an overtone, a combination band, then the coupled vibration is called Fermi Resonance. Again, only certain combinations are allowed. Fermi Resonance is often observed in carbonyl compounds. So the carbonyl compounds are carbon, double bond, oxygen. So like aldehyde, ketone, carboxylic acids, esters. Although rotational frequencies of the whole molecule are not infrared active, they often couple with stretching and bending vibrations in the molecule to give additional fine structure to these absorptions, thus further complicating the spectrum. So you often see that the IR spectrum is very complicated and we cannot assign all of the peaks, such like in NMR spectrum we can assign every single peak, but that's not possible in IR spectroscopy. We cannot assign all of the peaks, but we can definitely assign major peaks in the IR spectrum. So one of the reasons a band is broad rather than sharp in the infrared spectrum is rotational coupling, which may lead to considerable amount of unresolved fine structure. Now, next topic is bond properties and absorption trends. Let us now consider how bond strength and the masses of the bonded atoms affect the IR absorption spectroscopy frequency. For the sake of simplicity, we will restrict discussion to a simple heteronuclear diatomic molecule, means having two different atoms, such as HCl. HCl is a heteronuclear diatomic molecule because it contains two atoms, H and Cl. A diatomic molecule can be considered as two vibrating masses connected by a spring. So consider this is a spring. So on one side we have a chlorine and on other side we have a HCl. The bond distance continually changes, but an equilibrium or average bond distance can be defined whenever the spring is stretched or compressed. So if you stretch this spectrum or you compress this spectrum beyond this equilibrium, the potential energy of system increases. As for any harmonic oscillator, when a bond vibrates, its energy of vibration is continually and periodically changing from kinetic to potential energy back again. The total amount of energy is proportional to frequency of the vibration. So E energy of oscillation is directly proportional to E V oscillation, which for a harmonic oscillator is determined by the force constant K of the spring or its stiffness and the masses m1 m2 of the two bonded atoms. The natural frequency of vibration of a bond is given by equation. So this is the important equation. Nu bar is divided by 1 2 pi c K divided by mu, which is derived from Hooke's law for vibrating springs. The reduced mass mu of the system is given by mu is equal to m1 m2 divided by m1 plus m2. K is constant that varies from bond from one bond to another. As a first approximation, the force constants for triple bonds are 3 times those of single bonds, whereas the force constants for double bonds are twice those of single bonds. So for triple bond, like this is the triple bond, so force constant is bigger, greater than double bond, and the force constant of double bond is greater than the single bond. The two things should be noticeable immediately. One is that stronger bonds have a larger force constant K. So if the bond is strong, then the K will vibrate at higher frequency than weaker bonds. The second is that bonds between atoms of higher masses, larger reduced mass, vibrate at lower frequencies than bonds. So strong bonds, so stronger bonds, that's the point. So strong bonds will have a larger force constant K and vibrate at higher frequency. So the higher frequency. But if the second is that bonds between atoms of higher masses, if the mass is high, like 100, 200, and vibrate at lower frequency, the frequency will be lower. That is important. Again, I'm repeating, strong bonds will vibrate at higher frequencies, weaker bonds will vibrate at lower frequencies. Bonds that have higher masses will vibrate at lower frequencies, lighter ones will at higher. For example, in general, triple bonds are stronger than double or single bonds between same two atoms and have higher frequency vibration. So triple bond gives the peak at 2150 centimeter, double bond gives peak at 1650, and single bond gives peak at 1200. And in this direction, the K is increasing force. The CH stretch occurs at about 3000 per centimeter. As the atom bonded to carbon increases in the mass, the reduced mass, the frequency of vibration decreases. That's important. So CH has a mass of 13, so the frequency is higher, 3000. So if you see the mass of CC compared to CH, so the mass of CC is higher, hence the frequency is lower. Here the frequency is higher. If you compare CO with CC, the CO has higher mass, so the frequency will be lower, 1100. If you compare CCl, it will appear at 750 per centimeter because the mass of carbon and chlorine bond is higher. Similarly, the mass of carbon and bromine bond is higher than carbon-chlorine. It appears even at lower frequency, 600. The mass of carbon and iodine bond is higher and it appears even at lowest frequency, so 500. So the concept of this is that if the two atoms have the higher mass, the frequency will be lower for them. Okay. Bending motions occur at lower frequency than the typical stretching motion. So as you know, sometimes you are see in the IR spectrum STR and bending. So if there is any bending vibration, that is going to appear at lower frequency, okay, and stretching frequencies are going to appear at higher. So stretching higher frequency, they will appear at higher frequency, and bending will appear at lower frequency. CH stretching, that is appearing at 3000 because it's stretching, and this one is appearing at lower frequency at 1340. Hybridization affects the force constant K. Also, bonds are stronger in the order sp, sp2, sp3. So the sp will appear at highest frequency, then sp2, and then sp3. So for example, this is alkyne triple bond, that will appear at highest frequency, 3300 per centimeter. sp2 will appear at 3100, and sp3 will be lowest. So this is lowest, and this is highest, and this is medium. Okay. Resonance also affects the strength and length of a bond and hence its force constant K. Thus, whereas a normal ketone has its carbonyl stretching vibration at 1715, a ketone that is conjugated with a double bond lower frequency. So with resonance, frequency is lowered. Okay, so this ketone is involved in resonance like this. This bond goes here and this bond goes to the oxygen. The oxygen gets negative charge and this is positive, and this is the resonance arrow. And due to resonance, the carbonyl stretching which appear normally at 1715 per centimeter will appear at 1675 to 1680. So due to resonance, the frequency is lowered. Resonance has the effect of reducing the force constant K and the absorption moves to a lower frequency. The Hooke's law expression given earlier may be transformed into a very useful equation as follows. So this is the equation: nu bar is frequency in per centimeter, c is the velocity of light or speed of light, that is 3 into 10 power 10 centimeter per second, k is the force constant in dynes per centimeter, masses of atoms in grams, and masses of atoms in AMU. Removing Avogadro's number from the denominator of the reduced mass expression mu by taking its square root, we obtain this expression. Here the calculation of stretching frequencies for different types of bonds. So if you want to calculate frequency for stretching CC double bonds, so you put this formula and you will get this answer: experimental, calculated, experimental, calculated, experimental. A new expression is obtained by inserting the values of pi and c. That's the new expression: 4.12, and our atomic weights. This is for the atomic weights, and k is a force constant. This equation may be used to calculate the approximate position obtained in the IR spectrum by assuming that k for single, double, triple bond is 5, 10, 10 respectively. Table 2.2 gives a few examples. Notice that excellent agreement is obtained between experimental values given in the here. However, experimental calculated values may vary considerably owing to resonance, hybridization, and other effects operate in organic molecules. Nevertheless, good qualitative values are obtained by such calculations. I hope you understood this lecture about IR spectroscopy, and I will be making more videos about IR spectroscopy as well as UV visible mass spectrometry and NMR. Keep watching this channel. Thank you. Take care. Bye.